Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be talking about evolution. So we've spent a lot of time looking at geology, a lot of time looking at earth science and the continents. So now it's time, I don't know why I said fine, time to finally transition into evolution and more information about its discovery. So most people are aware that Charles Darwin is the person that is responsible, primarily at least, for the theory of evolution. Now, what he was doing was observing differences between different species on the Galapagos Islands. So this is his journey. And he went all over, again, so New Zealand, Australia, all over through the Indian Ocean, past the South Africa, going all over the place, right? So he was all over the place, but the Galapagos Islands are right here off of the coast of South America and Central America. And what he noticed were that there are variations, and variations are differences in physical characteristics, and variations help organisms survive in their environment. So even though you might find turtles or tortoises all over the place, they had different adaptations that allowed them to survive in the environment they were given, right? In the environment that they found themselves in. Those adaptations and those variations were extremely important to their survival. And so, like he said, or like I already kind of said here, he noticed that adaptations, which are features that allow organisms to better survive in their environment, played a huge role. So it wasn't a coincidence that you would find something like and here are some birds, right? Like a piplup, so a penguin, right, in an area where it is colder, and right, they can't even fly, but they're birds. But they don't need to. They have flippers basically so that they can swim. And so the idea seems to be, right, that they have adaptations that allow them to survive better than other organisms in that environment. And so that takes time, though. That doesn't just happen overnight. So evolution is the change in inherited characteristics of a population over time. And it can happen quicker than you'd think. I'll show you a video clip in a little bit. But it also normally takes a long, long, long time. When people hear the word evolution, they immediately think, oh, millions and millions of years. It doesn't have to be millions of years. It's just those adaptations that we think of that are like, I don't even know, like eyes, or even though that didn't even take that long evolutionarily to evolve. In fact, it's one of the earliest adaptations animals had. Anyway, I'm getting off track. But the whole point is that it can happen quickly. Usually it takes many generations. But when people think of evolution, that tends to be where they go. Okay. So where did he formulate his idea? It's not like he just came up with this all on his own. So artificial selection is a huge deal. It is the way that we get and select, particular traits that we like in our organisms and in our animals and plants and stuff. And we breed those until they become common. And so he felt like selection could explain the varieties of animals that we see today. And so, right, think about it. Dogs are all technically the same species, but they have a variety of different traits. And those traits have been bred over the course of many generations just to do particular things. So retrievers, I have a golden retriever. So retrievers were bred to retrieve things. So they have like 2 layers of fur so they can swim. They instinctually have all of these different adaptations also, not just mental ones, but physical ones that make them different and look different than other breed of dogs. And he felt like selection could explain the variety of animals that we see today, except, of course, we're the ones selecting the different traits in artificial selection. So he was just thinking, okay, great, maybe there is like who or what is doing the selection becomes the important part. And so he felt like the environment must be the provider in this situation. The environment must selectively pressure particular traits. And again, it is removed from anybody's bias. It is instead the environment. And as the environment changes, maybe different traits become more advantageous. So this is really getting to the idea of natural selection. So natural selection is a process by which organisms that are the most suited for the survival in their environment survive and reproduce. A good example of that happens very quickly is antibiotic resistant bacteria. And so here we have our non-resistant bacteria, and they are making a ton of copies of themselves, billions and billions and billions. And all it takes is one little bacterium to have a mutation that allows it to basically be drug resistant. And eventually, what will happen is all of the old type of bacteria will die off, but all that will be left will be the mutant bacteria, the bacteria that have that adaptation. And so before you know it, you have a drug resistant bacteria. And so a lot of times people kind of like to say that this is an example of survival of the fittest. And so when they say fittest, I think a lot of times people don't understand that they're talking about fitness. And fitness is a measurement of how well an organism can survive and reproduce. And so fitness can be a lot of different things. It can be, maybe the fur color, whether or not they have wings, if they have webbed feet, how big the organism is. All of these things can play a role into their fitness. And so again, we have snow foxes or Arctic foxes who in the wintertime have a coat that is basically snow white. And then in the springtime, their color changes to more of that of like a kind of a grayish color to blend in with whatever is beneath the snow, right? And so that would be a good example of an adaptation that would lead to increased fitness for that particular organism. And now here is our kind of sped up version of how quickly natural selection can happen.
So what we ended up building was basically a petri dish, except that it's 2 feet by 4 feet. And the way we set it up is that there are 9 bands, and at the base of each of these bands, we put a normal petri dish thick agar with different amounts of antibiotic. On the outside, there's no antibiotic. Just in from that, there's barely more than the E. coli can survive. Inside of that, there's 10 times as much, 100 times, and then finally the middle band has 1,000 times as much antibiotic. And then across the top of it, pour some thin agar that bacteria can move around in. The background is black because there's ink in it, and the bacteria appear as white. First, you see they spread in the area where there's no antibiotic, up until the point they can no longer survive. Then a mutant appears on the right. It's resistant to the antibiotic, it spreads until it starts to compete with other mutants around it. When these mutants hit the next boundary, they too have to pause and develop new mutations to make it into 10 times as much antibiotic. Then you see the different mutants repeat this at 100. And after about 11 days, they finally make it into 1,000 times as much antibiotic as the wild type can survive. And so we can see by this process of accumulating successive mutations that bacteria, which are normally sensitive to an antibiotic, can evolve resistance to extremely high concentrations in a short period of time.
So again, that just took 11 days. All right, so many generations, though, are what we're talking about here. So that was over the course of 11 days, but there were many generations of bacteria that were reproducing and evolving over the course of those 11 days. So adaptations could successfully, basically, over the course of a long time, effectively change one species into a slightly different species. And we know this because of a couple of different things, but one of the biggest ones is nylon eating bacteria. Nylon is a synthetic material and it didn't exist I'm not sure when nylon was actually invented. I think it was like the 1950s though. And so they found in a nylon chemical plant where they dumped their nylon waste into this pond area, this like outflow, bacteria that were surviving off of eating this nylon. And since nylon didn't exist before whatever date, that kind of led us to believe that, wow, that bacteria evolved super quickly. It must have been an original bacteria that couldn't consume nylon. And then it was able, over successive generations, because of probably the amount of nylon that was there, it was like, so over the course, the environment selectively pressured the bacteria to develop these adaptations. Italian wall lizards, we'll talk about them a little bit more later on. But Italian wall lizards are a super cool example. They were not native to a particular island. And then what they decided to do was to put these lizards on this island where their original food source was in scarce supply, just to see if they would survive and what would happen. And what they found when they went back years later were that these lizards had almost entirely different digestive systems, and were succeeding. Multicellular algae, we'll look at that in a second. But that's another good example of, again, species evolving and slowly changing into different species. And so here's some multicellular algae. And so it's pretty crazy, but like this is day one. You have this individual kind of algae, right? There you go. That's day one. And then what starts to happen though, when we fast forward, is after day 350, instead of developing as these individual little algae that have to compete with each other, they started to form these colonies. And so you end up kind of getting multicellular creatures from originally unicellular items. And this is again just after day 350. So this is about a year of natural selection going on before we ended up with these clumps of algae instead. And so Darwin also proposed, right, that living species are descended with modification, of course, from common ancestors. And so, again, even though I've been kind of using the term change into, what we're not saying is that one animal turns into another. We're not saying a frog turns into a lizard. No. What we're trying to say is that they share a common ancestor. So in the previous example, I'm not saying that that algae after 350 days is a totally different species of algae than was there before. But it is slowly becoming that, right? It's leading down that pathway. We're not saying that every antibiotic resistant strain of bacteria is a unique species, but it seems like it is going down that road where enough mutations are accumulating that before you know it, they are not the same thing. And so what we're trying to say when we are talking about common ancestors are that we're not saying cats turned into dogs or whatever, but all cat-like creatures must have derived from a cat-like ancestor. And so there's a way of studying that, and we call that phylogeny. So phylogeny is the study of evolutionary lineage among a group of species. And it can get pretty crazy. So here is a phylogenetic tree with a lot of things missing, but each little fork in the road that we see here is a different trait or a different attribute that all of the descendants that follow from that have. So we have our hypothetical common ancestor all the way at the bottom here. Everything above this has mitochondria and a nucleus. Everything. From this branch, everything up here has at least, chloroplasts. Everything above this has organs. Everything above this has a nervous system. Everything above this, has feathers. And so obviously we can piece together things over time and over the fossil record, right? Looking at things that have gone extinct. And there are certain ones that we're not entirely sure of, and they're hypothetical common ancestors. And so we like to, um, I'm putting them in red here, but they're hypothetical in the sense that, okay, great, we haven't found a fossil, we haven't found any evidence so far that, it exists, but, we're putting in a placeholder. It's kind of like on the periodic table, right? We have all of these spots. And I mean, technically now we filled in the entire periodic table, but eventually we're going to need to add another period to the periodic table because we're going to, make a heavier um, uh, element with a higher atomic number. So we put in little placeholders for them. Same thing with hypothetical common ancestors. We put them in and we say, great, now we got to find them. Now we've got to look for them. Now we have to actually do work and prove that that is, there. And maybe it isn't. And so maybe the tree of life looks a little bit different from this. And that is totally and completely okay because science just follows evidence.